Good morning, dear students. Today's session we are going to see about how to demonstrate sampling theorem. So sampling theorem states that the sampling frequency should be greater than or equal to twice the maximum frequency. There are two ways of demonstrating the sampling theorem, that if you don't sample at the higher frequency, distortion will happen. There are two ways to demonstrate this. One is in the time domain, another is in the FFT domain, that is frequency domain. So in time domain, what we are going to do is, we are going to generate a signal of certain frequency with higher sampling rate and lower sampling rate, and to visualize the output waveform, how it is distorted in the time domain. That is, x-axis is equal to time domain, right? So look at this. First, how long we want the signal that we are describing. That is 2 into e power minus 3 is the time duration for which we need the signal. And this 10 e power minus 6 is the increment. That means we need samples every 1 microseconds. That is, sampling frequency is 10 megahertz. That is 10 microseconds we want every sample. Second one is TS is equal to same signal we are going to generate with 1 millisecond sampling time. See, 1 millisecond sampling time is 1 kilohertz, and 10 microseconds, which is higher frequency, 10 microseconds, which is 10 megahertz. Here, this is just 1 kilohertz, right? So see that same duration, time duration for which we need the signal is 2 into e power minus 3, here 2 into e power minus 3, which is 2 milliseconds. Okay. So the signal we want to generate is f is equal to 1000 hertz, right? So two different time instants we have defined. One is with the T sampling, which is 10 megahertz sampling, and another with this TS, which is 1 kilohertz or 10 kilohertz sampling, because 0.1 into e power minus 3 may be 10 kilohertz sampling. So this is the higher sampling. This is the higher sampling, and this one is the lower sampling. Okay. So in higher sampling also we will plot, and lower sampling also we will plot. It is in time domain, just to see the T and TS, right? So you see that, so the one with the clipped output waveform is the lower sampling rate, that is 10 kilohertz. The higher one is 1 megahertz, right? So this is the distortion in the time domain we can visually see, right? So we have generated a 1 kilohertz signal here. Let us generate what is the signal? Some 9000 kilohertz, that is 9 kilohertz signal. Same thing we are using. So when you do that, plot the waveform, and because lower frequency waveform we have 2 cycles. This is higher frequency waveform, so many cycles we have, right? So many cycles, the blue one is many cycles, and this one you see that orange color, which shows clipping, right? Which shows clipping. F into TS, okay, that is clipping. So clipping is, I think B, C, fine, okay, 9 kilohertz. So this is clipping, where very much clipping, it is visibly noticed. So this is the way of proving the sampling theorem in time domain. That is, proving means we are saying that less the sample rate, distortion is more. Okay, fine. So next, what we are going to do is, we are going to prove that in frequency domain. So in converting the time domain to frequency domain, what we do FFT, fast Fourier transform or Fourier transform, right? So here, instead of only one signal generated above, we are generating 500 hertz, 1500 hertz, one more 1500, 2000, 3000, 4000, 5000, 6, 7, 8. So totally 10 signal, but 1500 hertz is twice. So 9 signal out of which. So we have the highest signal is 8000. So our sampling rate should be greater than the maximum frequency. So which is 16,000. So let us assume that 18,000 we will give here. A little bigger more, right? Oversampling. So this is Fs, t is equal to 1 by Fs. So we want the signal for 1 seconds, right? 1 second. Previously we had the time rate for duration for how much? 2 milliseconds we have done, but yeah, 1 second. And then we need the number of samples for finding out the FFT. How do you find out number of samples? See, Fs is what? Samples per second. T is what? Seconds. So samples per second into seconds, seconds get cancelled. This is giving number of samples. N is giving number of samples, right? So then we are designing all the frequencies. Frequencies, we know the formula. 2 pi f is omega, 2 pi ft is the signal. Pi we are taking from the NumPy package. This pi is we are taking from the NumPy package, only this thing, right? And next one, everything, same formulas, and we are generating the signal. So once generating the signal, we are adding all the signals together, y1 plus y2 plus y3, because in order to have some minimum frequency signal and maximum frequency signal, we are generating all. Next, we are finding out the FFT using this, right? So FFT using this, then we are plotting this, okay? So let's plot now. So this is the time domain signal, and the time domain signal, because we are taking it for 1 second, it is an 8,000 kilohertz, it is very dense, and you don't see any sinusoidal waveform here. See that we have 9, totally 10, y1 to y10, but now what we are giving, well, 2,500 signals were there. So 9 components, 1, 2, 3, 4, 5, 6, 7, 8, 9 components. See, this component is 500, 10, 100, 200, 300, 400, 500. This is 500, right? This is 1000. This is 2000. So in between 1500. So 2000 is also one is there. 3000 also one is there. Everything very clearly we have recovered. Whatever was in the time domain, how we generated, everything is recovered in FFT, right? So this is oversampling. Let us play with some undersampling. You also heard a sound in between, right? So the sound, now you try to do that. Now let me give sampling frequency of 10. So at least up to 5 kilohertz it should recover. We'll see. See, this signal, this sound is different from that sound, right? See that only 2 signals we have recovered, 500 and even 1500. Only these 2 signals we have recovered, other things are not even there, right? So this is called a distortion, right? Undersampling frequency. So even 3, 4 also have not come. If many are there, it will come, right? Now critical sampling frequency we will do. See this waveform, sound. So critical sampling 3, 4, 5, 6, 7, 8. 1 is missing, I think. That last component 8 kilohertz is missing. Another everything is all present, right? So we should have greater than or equal to twice the maximum frequency. Maximum frequency is our maximum frequency is 8 kilohertz. Twice the maximum frequency is 16 kilohertz. But at 16, there is a small problem because it is a combination of only 10 signals. If it is a combination of many more signals, that holds good. Now we have to little more sampling, we have to do that, right? So we saw undersampling, very less number of frequencies are recovered, and critical sampling, this one, everything is recovered and the last frequency is a small distortion. And oversampling, everything is very well recovered, right? So you know that if you don't sample it with any signal with greater than or equal to twice the maximum frequency, you will be in trouble. That is, you will not be able to recover all the information after you bring into digital domain, right? So this is how we need to prove. Summary is, we can prove in time domain also. Time domain, we can clearly see the distortion. There we have to consider only one signal. If you consider multiple signals, the distortion cannot be viewed even in time domain also. That is why I considered only one signal, which is 10 kilohertz or 1 kilohertz. I don't remember now, right? You can go ahead and see that. F is equal to 1000 only, I think. 1000 and 9000 we saw that only one frequency, right? Now for FFT frequency domain, we can consider any number of signals, right? Okay. Thank you.